And welcome again. Here is one more problem in this series that we are calculating the dipole moment of a neutral system, and this time we are going to calculate the dipole moment of a half ring, semicircular ring. It's half, easier to speak. And the statement of the problem is in the center of a semi ring of radius r, there is a point charge minus q. You can see it here. Yes. And the semi ring is charged with linear charge density proportional to some cos theta. Theta is the azimuth angle, you can see here. And where theta is the angle between the radius vector, that is the position vector of the point under consideration, and the symmetry axis of the system, z. That is what we call it as an azimuth angle. The total charge of the semi ring is plus q. Yeah. So net charge is 0. Determine the dipole moment of the system. Find in dipole approximation the potential phi z with potential normalization phi infinity equal to 0. Infinity पर हमें potential का value 0 लेना है. And the electric field strength on the z axis, as z is much greater than r. You can do so many things with this problem, but I'm focusing on how to find the electric dipole. So according to the conditions of the problem, lambda theta, that is the charge distribution over the ring in terms of theta, is something we can write at lambda naught cos theta. Of course, here lambda naught is from the condition. Lambda naught is basically a constant, but from the condition that the total charge of the semi ring is equal to plus q, you can calculate plus q as well in terms of or if you like to calculate, just calculate the value of lambda naught first from the given condition that the total charge of the semi ring is equal to plus q. And we can do this by writing q will be equal to integration of lambda theta dl, and dl is here is nothing but if angle is theta, dl, to find dl we can take a small angle d theta here, so that this length become r d theta, and this is the value of dl here. And do the next of the things. You can write here q equals simply lambda theta. In place of lambda theta you can write lambda naught cos theta, and for dl you can simply write r d theta, and its limit gone from minus pi by 2 to pi by 2 to pi by 2, and then you can solve, and you will get here simply as this thing becomes 2r lambda naught, this integration, and since q is equal to 2r lambda naught, that means you get the value of lambda naught is equal to q upon 2r. So we got our lambda naught. Now determine the dipole moment of the system, and we already know that the system is electrically neutral, so its dipole moment can be found from the formula simply as integration of lambda r multiplied by r dl. And you know, due to the symmetry of the system is symmetric, it is clear that the projection of dipole moment on the x-axis is 0. and the dipole moment of the system is directed along the z axis. So let us select on the semi-ring a small section of length rd theta, and its charge being lambda theta rd theta. On this particular thing, this will be lambda theta, rd theta will be the charge on this section, and it is of course located at a distance r from the point charge minus q, and the projection of the position vector, that is it, on this of this section on the z axis is equal to r cos theta, projection of position vector, and we can integrate over the angle theta in the range from minus pi by 2 to pi by 2 to get it. So I am calculating here P, that is basically Pz, and that can be written as lambda theta r square, r is here r, and dl is rd theta. So we can get something like this, and limits are from minus pi by 2 to pi by 2, and so we can write here lambda naught from limits of the integration from minus pi by 2 to pi by 2 cos theta, of course, and then r square, and r square, this in this case we missed something. We should have written here, because we are calculating Pz, we should have written here dz, and that dz becomes r cos theta d theta. Dz here is r cos theta d theta. That means we can write here r square one more cos theta d theta, and then we can calculate the integration, and it will be something like lambda naught minus pi by 2 to pi by 2 r square cos square theta d theta, and we know how to solve it. And this is simple to calculate, and you will get your result, and result is q r pi upon 4, and this is the dipole moment, and I guess you can calculate if once you calculated the dipole moment of the system, you can also calculate the potential of the system on the z axis, and we know we can use the formula for phi z in terms of dipole moment, that it is simply, it can be written as 1 upon 4 pi epsilon naught p dot r by r cube, and this becomes 1 upon 4 pi epsilon naught pz. P dot r here is pz by z square, and I guess we have qz, and you can write it here, and you will get your result as qr by 16 epsilon naught z square. And how can we calculate the electric field on the z axis? We can use this formula. Instead of going through the basics, we can use this formula. Ez can be simply written as 1 upon 4 pi epsilon naught 3 p dot r. The formula was previously determined or calculated or derived, whatever you would like to call it, minus vector p divided by r cube. We already have this formula, and you can use it. And the value of p dot r is simply pz. The position vector r you can write here, and you will get your result simply as 1 upon 4 pi epsilon naught 2p vector divided by z cube. And well, you can get the result as unit vector along z axis is k, and like this you will get your result. So after calculating the dipole moment, you can easily calculate the electric field and potential and try to calculate them. Thank you very much for watching.